Hi, good day, everyone. We're just going to do a short video today on chapters 3, specifically 3.2, 3.3, and if we have the time, we'll get to 3.4. Okay, so this entire section covers predicates and quantified statements, right? And of course, as well, statements with multiple quantifiers, right? But first, we have to start with one statement, right? And then once we understand that properly, we'll be able to do a combination of them like we did in last section. So just like the last section where we learned what are statements, statement forms, arguments, argument forms, etc. Right? And then we learned one type, and then we learned all the connectives like and, or, not, and then we were able to bring them together. We are going to try to do the same thing here, right? We're going to start with one and then branch out and then do multiple of them. So first thing first, negations and quantified statements. We need to know that, if we recall from the last section, we'll remember that the negation of a statement is basically saying the opposite of what the statement claims to be. So for universal statements like all primes are odd, right? The negation of that statement that for all is that there exists one, right? So if I'm speaking about all in a set here, so the negation of the statement of the form for all x inside D, comma, q of x, and we spoke already in 3.1 what q of x represents, is logically equivalent to a statement of the form there exists x inside D. So therefore, the first part, if we look at it, we see that we are speaking about all of the x's, every single one. But in order to take the opposite of that, we speak about one thing in the set. So that's how we say there exists an x inside D such that, and then of course we have to negate q of x as well. So that's why we put negation of q of x, right? So based on what we did before in the last section in chapter 2 and to some extent 1, we may think that by negating all of it, we take nothing of the set, right? But that does not work in quantifiers. For all means that there exists one inside the set. So symbolically, we write it as this, the negation, and we have to remember to put our parentheses as well here. For all x inside the comma, so the way that we write this is very important, comma, q of x and close brackets. So this is equivalent to saying that there exists an x inside D, so the same thing like here, such that we negate q of x. So the negation of a universal statement, all are, or meaning for all here, this part here, is logically equivalent, right, to the statement some are not, or there is at least one that is not. So just like in the previous section where I gave you a bunch of equivalent statements for and, or, and not, you should make a note of these here as well. But these logical equivalent statements are for quantifiers, right? Quantifiers. The ones that were previously done were for logic and illogic tables, right? Note that when we speak of logical equivalence for quantified statements, we mean that the statements always have identical truth values no matter what predicates are substituted for the predicate symbols. And, so second part, no matter what sets are used for the domains of the predicate variables. So two conditions, unlike the one condition that we had for chapter 2. The general form of the negation of an statement follows immediately from the definitions of negation, right? So what we stated at the beginning, which is that we say the opposite of what we have. So for universal statements, so these are universal statements. So for universal statements, Like the statement I said at the beginning, all primes are odd. The negation of all primes are odd, right, is the statement there exists a prime that is not odd, right? There exists a prime that is not odd, or there exists a prime p such that p is not odd, right? So this is how we say it in words. A second example here is that there exists a triangle T such that the sum of the angles of T equals 200 degrees. So if you had to negate that, we said for all triangles T, comma, and we have to put the comma, right? Because remember we said here, look, we have a comma here. So the way that we write it here is very, very important. The sum of the angles, so we keep the words that we had in the original statement the same. The sum of the angles of T does not equal 200, does not equal, because remember, we have to negate that part as well, because we have negation of Q here as well, right? So that is very, 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 very important. So another an equivalent statement could be something like, so we have there exists a triangle. So if I said something else like some triangles have angles, okay, maybe I should write that down. So if I wanted to write something like some triangles, I'm just writing shorthand here because I don't have space, have angles summing to 200 degrees, right? What is the negation of this statement here? The negation of this statement is, so sum will turn to a different color. Sum will turn to all. We'll keep the word triangles. So all triangles have will now mean do not have. Do not have. Angles will remain the same. Angles summing to 200 degrees. Okay, so some triangles have angles summing to 200 degrees. So the negation, all triangles do not have angles summing to 200 degrees. So that's the negation, right? So if we had the original statement, right, let's write it in symbols for completeness. Yeah. So suppose that same question with the sum, right? If we had it in words, we would have something, sorry, in symbols, we had something like there exists an X. Let's keep these symbols the same inside D, such that Q of X, right? If this was the original statement, then the negation of it would be for all X. Okay. Inside D, comma, not Q of X. Okay? So just as an extra example. So these were universal statements. And what about conditional statements? Negations of universal and conditional statements. So before, in the previous part that we just did, we talk about from one thing or from all things, right, depending on the question, right, how we can negate them. Now, negations of universal conditional statements follow the same pattern to some extent at the beginning, where we have the for all part. However, the part that changes is this part here. P implies Q. So now we have These statements for conditional statements, negation of universal conditional statements, are of the form for all x, if p, then q, which is different from the last one where we had for all x. Pull up so you can see for all x inside D, not q. So now we have p implies q, right? Or if p, then q, right? So the negation of a statement, there exists an x such that p of x is true, but q of x is false, in symbols means that there exists an x such that p of x and not q of x, right? So just to be clear, the negation of the statement, there exists an x, so this is for conditional. The negation of a statement, there exists an x such that p of x is true, but q of x is false, right? Is that there exists an x such that p of x and not q of x. So if you want to write it in words, like here. An example, for all people, small p, if p is blonde, then p has blue eyes. So the solution is there exists, as we just said, a person, p, so one person, right, such that p is blonde and p does not have blue eyes. It has to be not, because not q, right? That's why we have not blue eyes here. If a computer program has more than 100,000 lines, then it contains a bug. There is at least one computer program, so a computer program, that has more than 100,000 lines and does not contain a bug. So not Q part. Okay, so that is very, very, very important. So another example, if a number is greater than, like we had the example here, if a number is greater than 2, okay, let me write it out. See if I can get some space right here. If a number is greater than 2, greater than 2, then its square is greater, than 4. So the negation of this statement would be that there exists a number. So question, answer, there exists a number, so 1, greater than 2, whose, you see the language of the sentence has to be grammatically correct as well, whose square is not greater than 4, full stop. Okay, so having grammatically correct sentences is also very important here, right? So back to this. So this part here from 15, 16, 17, and 18, right, is ready for your reading on your own time. And we'll move on now to 19. Remember, I spoke at the beginning of the first class and I said that there's some stuff that is ready there for your reading. Well, this is one of them. So now we're moving on to the vacuous truth of universal statements. So this entire section, what it's really talking about is that a universal statement, right, like we had before, is true if the premise, right, and we could call our premise something else like p of x or something, right, is false for all x. How can something be true if the premise is false, right? And this example here illustrates this very nicely. Suppose that a bowl sits on a table next to the bowl, and next to the bowl is a pile of 5 blue and 5 gray balls, any of which may be placed in the bowl. So this is it here. If 3 blue balls and 1 gray ball are placed inside the bowl from this set here, then the statement all the balls in the bowl are blue would be false. Why? Because we have one of them being gray, and we know that. Or suppose that we had nothing in the bowl. It was empty to begin with, right? That no balls are placed in the bowl. Then if I had a statement that all the balls in the bowl are blue, is that statement true or false? The statement is false if and only if the negation is true, right? And its negation is there exists a ball in a bowl that is not blue, but the bowl doesn't have anything in it. But the only way that this negation can be true is for there actually to be a non-blue ball, blue ball, sorry, in the bowl. And there is not. Hence, the negation is false, and so the statement is true by default. So this is showing you that we can say that it is true if the premise is false. The premise is false here, so we could say it's true. So if I had another statement, if this is too difficult to understand, if I had something like, if I said that all, right, all unicorns, right, are blue, or all of them, right? Forget about the bowl and the ball for now. If I said all unicorns are blue, then that statement is true if no unicorns exist. So the statement is all unicorns are blue, right? And I'm saying that that statement is true if no unicorns exist. But if I think about it, since there are actually no unicorns, then the statement itself doesn't fail. So therefore, the statement all unicorns are blue is considered true by default, right? I can't really show that, so I just take the statement as being true. So vacuously true. So now we have some variants of universal and conditional statements. So consider a statement of the form this here: for all x inside D, if P of x, then Q of x, right? So like what we had in the previous part. So what we are going to do here now is discuss the contrapositive, converse, and inverse. Now remember, in the previous section, chapter 2, we went through converse, contrapositive, and inverse, right? The rules that we learned there are with respect to logic and logic tables, right? This one that we're doing here is with relation to quantified statements, right? So don't get confused between the both of them. So the contrapositive now of the statement for all x, P of x implies Q of x, which is this part here, is the statement for all x. So be careful, right? Before when we had to take converse and the negation, we had to change this to there exist. Now we are keeping it as for all. So the contrapositive, so we have to learn this table, right? The contrapositive is for all x, not Q, implies not P. What does this statement tell me here? This statement number 1 tells me in words that the contrapositive is always logically equivalent to the original statement. Right? That's the contrapositive. The converse now. Same thing for all x again. But this time, if q, so we reverse it just like we did before, but we don't have the nuts in front of them. If q, then p. Right? So another way, I guess you can say this, I will keep it like this for now. Right? We'll keep it like this for now. We want to change this to too many equivalent forms because we already have so many. The last one is the inverse. Again, for all x, we keep it as it is, if p then q. However, we put negations in front of them. So by looking at number 2 and number 3, remember for number 1, we said that the contrapositive is always logically equivalent to the original statement. So if I look at number 2 and number 3, I see that neither, so I could say it in words, right? So this is important. So neither the converse nor the inverse, neither of them is logically equivalent to the original statement. And we can see this, right? By the way that it is set up here. Okay? So that is important for these two here. So let's look at these examples here. If a real number is greater than 2, then its square is greater than 4. So this is the formal version of the statement. For all x inside real numbers, or as x runs through the set of real numbers, if x is greater than 2, then x squared is greater than 4. Notice that it is strictly greater than, because it didn't say greater than or equal to. So if perhaps you were writing this and you put an equal sign here, that would be wrong, right? It would not be the same as this. So bear that in mind. So the contrapositive is for all x, so we keep the for all x part, but it tells me that I put not q and then not p. So I have to put x squared is less than or equal to 4, because it's the opposite of this. Then x is less than or equal to 2. So in words, I would say this as, if the square of a real number is less than or equal to 4, then the number is less than or equal to 2, right? The number, because we're speaking about a number here that we don't really know about, right? So that is very important, the way that we write it. So the converse and the inverse as well here is really left for you to look at. We have the same forms here and we rewrite it here. Another example, if you want to use, we can use back this example here we did at here. If you wanted to use this statement here, a shorter one, if that example was too difficult for you. The statement here, let's change the statement to make it easier to see. So I'm going to use part A. I'm just going to do an example like these here, because maybe this might be a little bit too difficult. Suppose I have this statement, write this out. Suppose I have this statement, I'm just going to write it here, right? If a person is blonde, then they have blue eyes. So the contrapositive of this would be that if a person does not have blue eyes, then they are not blonde. If a person does not have blue eyes, then they are not blonde. Right? So that is like an example of this one here, if this is too difficult for you. Okay, we'll see more examples on the tutorial sheets as well. The last part of this is the necessary and sufficient conditions. So we already went through this part in section 2, right? Necessary and sufficient conditions, where I spoke about if P is necessary for Q, etc., etc. When I gave you all the equivalent forms of P implies Q, right? These were already given there, and I said that it will come back in the second section. Well, this is actually the third section, and this is it here, right? So to understand this, just refer back to that section which we spoke about in chapter 2, for those of you who may have taken those notes, and that will be this part. So this is the end of 3.2. okay, the next section, or the next video, we will go to 3.3 and 3.4.